Welcome, my friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the sun's burning heart, where a single asteroid meets the most violent place in our solar system. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. A kilometre-wide asteroid drifts through the vacuum of space, its surface carved by 4 billion years of cosmic bombardment. The rock carries within its crystalline structure the memory of the early solar system metals forged in dying stars, organic compounds that never quite became life, water ice locked in shadow-cold crevices that have remained undisturbed since the Hadean eon. It tumbles slowly through the void, one rotation every 6 hours and 14 minutes, revealing faces of stone that have never known warmth beyond the faint touch of distant starlight. Each crater on its surface tells a story of impact, of smaller objects that struck and embedded their own histories into the asteroid's growing mass. Some of these craters hold deposits of rare earth elements, concentrated by the gentle chemistry of slow collisions over geological time. The asteroid's composition reads like a periodic table, written in stone, iron and nickel from the cores of ancient planetesimals, silicon and aluminum from the mantles of worlds that never grew large enough to hold atmospheres, carbon compounds that formed in the cold spaces between stars. The sun grows larger in the asteroid's predetermined path, no longer a distant star but a sphere of roiling plasma that fills an ever-expanding portion of the cosmic horizon. At this distance, still millions of kilometers away, solar radiation begins to affect the asteroid's delicate equilibrium. Ice sublimes directly from solid to gas without the intermediate step of melting, creating a faint coma of vapor that streams away like the breath of something slowly dying. The asteroid's surface temperature climbs past the melting point of zinc, then lead, then any substance that might have existed in Earth's patient geology. The pressure of solar radiation becomes measurable now, pushing against the asteroid's surface with the force of pure light. Photons carry momentum, and at this proximity to our star, that momentum accumulates into a tangible push that slightly alters the asteroid's trajectory. This radiation pressure, so gentle that it would barely move a feather on Earth, becomes significant in the vacuum of space where no air resistance exists to mask its effects. The asteroid begins to accelerate, pulled by the sun's immense gravitational field and pushed by the star's own light. Spectrographic analysis, were any spacecraft present to perform it, would reveal the asteroid's surface composition changing in real time. Volatile compounds, sulfur, phosphorus, organic molecules vaporize first, creating a thin atmosphere around the rocky mass that immediately streams away in the solar wind. This temporary envelope glows faintly in ultraviolet light, visible only to instruments sensitive enough to detect such subtle emissions against the overwhelming brightness of the approaching sun. The photosphere finally approaches that deceptively calm-looking surface that burns at 5,778 Kelvin, hot enough to vaporize any known material yet somehow appearing almost solid when viewed through the filtered light of solar telescopes. This outermost visible layer of the sun extends barely 500 kilometers deep, thinner proportionally than an apple's skin, yet it contains more energy than humanity has ever produced, consumed, or even imagined. The asteroid crosses this boundary without ceremony, like a grain of sand falling into an ocean of nuclear fire. Plasma immediately engulfs the rocky mass, and the physics of the encounter becomes almost impossibly violent. Here, in this realm of superheated gas, atoms move so frantically that electrons tear away from their nuclei, creating a conducting soup of charged particles that responds to magnetic fields with liquid grace. The asteroid's surface begins to melt, then vaporize, then ionize into its component elements in a cascade of phase transitions that happens faster than human perception could follow. The granulation patterns of the photosphere convection cells, the size of small countries rising and falling in precise 5-minute cycles, briefly distort around the asteroid's presence. These cellular structures, driven by the heat engine of the Sun's interior, carry energy upward from depths where nuclear fusion transforms mass into light. The asteroid's intrusion creates temporary asymmetries in these patterns, ripples in the otherwise orderly process of energy transport that propagates outward at the speed of sound through plasma. Silicon dioxide, the primary component of the asteroid's rocky matrix, dissociates into its constituent atoms at these temperatures. The silicon nuclei, stripped of all their electrons, join the plasma soup while the oxygen atoms contribute to the complex chemistry of stellar atmospheres. Iron and nickel, the asteroid's metallic core materials, ionize completely, their electrons moving independently through the plasma, while their nuclei become part of the Sun's vast reservoir of heavy elements. Scientists have calculated through sophisticated computer models that an object this size would survive perhaps 30 to 45 seconds in the photosphere before achieving complete dissolution. Only took the Sun 4.5 billion years to build such an efficient furnace. The irony rests quietly in the mathematical equations this asteroid, born from the same stellar collapse that created our Sun, returns now to the nuclear fire that originally forged its constituent atoms in the death throes of previous generations of stars. The temperature differential between the asteroid's relatively cool core and the surrounding plasma creates shock waves that propagate outward through the photosphere at supersonic speeds. These disturbances travel like ripples in a pond of light, carrying the asteroid's final signature toward the Sun's edge. The waves weaken with distance, their energy absorbed by the constant turbulence of solar convection, but sensitive instruments could potentially detect them as minute oscillations in the Sun's surface brightness. Magnetohydrodynamic effects become significant as the asteroid's metallic components interact with the Sun's magnetic field. The field lines, normally invisible rivers of magnetic force that arch high above the photosphere, respond to the sudden introduction of conducting material by reconnecting and reforming in complex patterns. These magnetic reconnection events release stored energy in brief, intense flashes that contribute to the overall dynamics of the solar atmosphere. One profound mystery persists in the plasma physics of this encounter, the exact mechanisms by which the Sun's magnetic field lines respond to such sudden introductions of foreign conducting material remain incompletely understood. Theoretical models suggest cascading reconnection events, where field lines snap and reform in fractal patterns, releasing stored magnetic energy in bursts that contribute to the heating of the corona above. The asteroid becomes a temporary catalyst for phenomena that solar physicists continue to study through computer simulations and spacecraft observations. Time dilates strangely in this environment, where the normal rules of matter and energy bend toward their extreme limits. The photons created by the asteroid's dissolution, light born from the conversion of matter in the Sun's nuclear furnace, now mixed with light from the asteroid's complete destruction, will take thousands of years to random walk their way outward through the Sun's dense interior. These photons will scatter countless times off free electrons and nuclei, each scattering event changing their direction randomly, before finally escaping as visible light that will someday warm distant worlds. The photosphere continues its ancient rhythm, essentially unperturbed by this brief addition of foreign matter that represents less than a billionth of the Sun's total mass. Convection cells rise and fall with metronomic precision. Magnetic field lines twist and reform according to the dictates of plasma physics. And the Sun's surface temperature holds steady at exactly the temperature required to sustain the delicate atmospheric chemistry that makes life possible on a small blue planet orbiting 93 million miles away. The asteroid's remnants pass beyond the photosphere into the chromosphere, that thin intermediate layer where the Sun's atmosphere begins its transformation from merely hot to impossibly energetic. Here, in a region extending barely 2,000 kilometers above the visible surface, temperatures paradoxically increase with altitude, climbing from the photosphere's 578 Kelvin to nearly 20,000 Kelvin at the chromosphere's upper boundary. This temperature inversion defies intuition. Moving away from a heat source should mean cooling, not heating yet. The chromosphere burns hotter than the surface below. What remains of the kilometer-wide object now exists as a cloud of ionized atoms, each nucleus stripped of its electron shell and moving independently through the increasingly tenuous solar atmosphere. The asteroid's silicon atoms, once locked in crystalline matrices that formed over millions of years in the asteroid belt's patient cold, now race through space at velocities that would carry them from New York to Los Angeles in under a second. Their kinetic energy alone exceeds the binding energy that once held continents together on long-vanished worlds. Hydrogen dominates this region of the Sun's atmosphere, comprising roughly 73% of the chromosphere's mass. The hydrogen atoms here exist in a state of constant excitation, their single electrons jumping between energy levels as they absorb and emit photons in the deep red wavelength of 656.3 nanometers. This specific color, the alpha line of the hydrogen Balmer series, paints the chromosphere in shades of crimson that become visible only during solar eclipses, when the moon's shadow blocks the photosphere's overwhelming brightness. The asteroid's carbon atoms, once part of organic compounds that might have seeded life on some distant world, now contribute to the chromosphere's complex emission spectrum. Carbon ions, missing several electrons, emit characteristic wavelengths of ultraviolet light that spacecraft instruments can detect and measure. These spectral lines serve as fingerprints, allowing solar physicists to trace the asteroid's dispersal through the Sun's atmosphere with remarkable precision. Each element announces its presence through its unique pattern of emitted light. Spicules rise from the chromosphere's lower boundary like grass blades made of plasma, each structure reaching heights of several thousand kilometers before falling back toward the Sun's surface. These jets of hot gas, discovered through high-resolution solar telescopes, erupt at velocities approaching 30 kilometers per second, fast enough to escape Earth's gravity entirely. The asteroid's atoms become entrained in these spicular flows, carried upward on currents of magnetized plasma that follow the invisible architecture of magnetic field lines. The chromosphere's density measures approximately 1/10,000th that of Earth's atmosphere at sea level, so tenuous that it would qualify as an excellent vacuum by terrestrial standards. Yet this near emptiness teems with activity invisible to human senses. Acoustic waves generated in the photosphere's convection zone propagate upward through the chromosphere, their energy gradually converting from sound into magnetic oscillations that will eventually heat the corona above. The asteroid's dissolution adds brief perturbations to these wave patterns, like dropping a stone into a pond of light. Magnetic field lines thread through the chromosphere in complex geometries that change constantly as the sun's internal dynamo shifts and evolves. These field lines act as guides for charged particles, channeling the flow of ionized gas along invisible highways that arch high above the solar surface. The asteroid's metallic components, iron, nickel, cobalt, become caught in these magnetic streams, their motion constrained to follow the field line's curved path through three-dimensional space. The chromosphere's temperature structure presents one of solar physics' enduring puzzles. Heat should dissipate with distance from its source, yet this atmospheric layer grows hotter with altitude, reaching temperatures that approach those found in the cores of other stars. Current theories propose that magnetic waves, generated by the turbulent motion of the photosphere below, carry energy upward and deposit it as heat through a process called magnetic reconnection. The asteroid's passage briefly disrupts these energy transport mechanisms in ways that remain difficult to model accurately. Helium becomes significant in the chromosphere's composition, making up approximately 25% of the atmospheric mass. This helium exists primarily in its neutral state, though increasing numbers of helium atoms lose one electron to become singly ionized as temperatures climb toward the transition region above. The asteroid's original helium content captured from the solar nebula during the early solar system's formation merges with the Sun's own helium inventory, adding an infinitesimal fraction to the reservoir of fusion products created in the stellar core. Chromospheric heating mechanisms operate through processes that remain partially mysterious to contemporary astrophysics. Magnetohydrodynamic waves, generated by the convective motions of the photosphere, propagate upward and steepen into shock waves that dissipate their energy as heat. Magnetic flux tubes, twisted by the differential rotation of the Sun's surface, store energy that releases suddenly when field lines reconnect and snap back to lower energy configurations. The asteroid's atoms become witnesses to these fundamental processes, their emission spectra recording the signatures of heating events too brief for human instruments to capture directly. Time scales in the chromosphere span from seconds to hours, depending on the phenomenon under observation. Spicules form and dissipate in minutes, while larger magnetic structures persist for hours or days. The asteroid's dispersal occurs on intermediate timescales, its constituent atoms spread through volumes of space larger than Earth within the first few minutes after dissolution. Yet the complete mixing with the chromospheric medium requires several hours of diffusion and magnetic transport. The transition region looms above, where temperatures will jump from the chromosphere's 20,000 Kelvin to the corona's 2 million Kelvin, across a boundary layer barely 100 kilometers thick. This represents one of the steepest temperature gradients known in nature, comparable to moving from Antarctic ice to molten steel across the width of a single city. The asteroid's atoms prepare for this transition by losing more electrons, their ionization states increasing as thermal energy strips away the remaining electron shells. Energy balance in the chromosphere depends on the delicate equilibrium between heating and cooling processes. Radiative cooling, primarily through hydrogen and helium emission lines, removes energy from the system while magnetic heating mechanisms add energy back. The asteroid's contribution to this energy budget remains negligible on a global scale, yet locally, its presence creates brief imbalances that propagate outward as waves and disturbances in the plasma medium. The chromosphere serves as a laboratory for plasma physics under conditions impossible to replicate on Earth. Magnetic field strengths here reach several thousand Gauss thousands of times stronger than our planet's magnetic field, while particle densities span ranges from the best terrestrial vacuums to the density of water vapor. The asteroid's atoms experience physics at these extremes, their behavior governed by equations that describe matter in states of ionization and temperature that exist nowhere else in the solar system. Red light from hydrogen alpha emissions creates the chromosphere's distinctive color signature, visible to specialized solar telescopes equipped with narrow-band filters. This deep crimson glow, reminiscent of heated iron in a blacksmith's forge, results from electrons dropping from the third to the second energy level in hydrogen atoms. The asteroid's hydrogen content, originally incorporated as water ice and hydrated minerals, now contributes to this cosmic neon sign that announces the presence of the Sun's middle atmosphere to any observer equipped with the proper instruments. The asteroid's dispersed atoms enter the corona, crossing the transition region, where temperatures leap from 20,000 Kelvin to 2 million Kelvin across a boundary thinner than the distance between neighboring buildings. This temperature jump occurs so abruptly that it defies conventional understanding of how heat should behave. In terrestrial experience, temperature gradients smooth out over distance. A hot stove cools gradually as you move away from it. Yet here, in the Sun's outermost atmosphere, the normal rules of thermodynamics bend around magnetic field lines that store and release energy through mechanisms still being discovered by solar physicists. At 2 million Kelvin, the corona exists in a state of matter so extreme that every atom becomes completely ionized. Electrons, torn from their nuclei by the violence of thermal motion, move independently through space at average velocities exceeding 1,000 kilometers per second. The asteroid's iron atoms, once part of metallic grains that condensed in the cooling disk around the young sun, now exist as bare nuclei carrying positive charges of 26-1 for each missing electron. These iron ions race through the coronal medium with kinetic energies equivalent to particle accelerator beams. The corona's density measures 1 trillionth that of Earth's atmosphere, making it a vacuum superior to anything achievable in terrestrial laboratories. Yet this near-perfect emptiness glows with X-ray emissions visible to space-based telescopes, its light generated by electrons spiraling around magnetic field lines in a process called synchrotron radiation. The asteroid's contribution to this emission appears as a brief brightening in the X-ray spectrum, detectable by instruments sensitive enough to measure individual photons against the corona's steady background glow. Magnetic field lines dominate the corona's architecture, creating structures that arch hundreds of thousands of kilometers above the Sun's surface. These field lines, invisible to the naked eye but revealed through their effects on charged particles, form loops and streamers that follow the magnetic topology generated by the Sun's internal dynamo. The asteroid's ionized atoms become trapped along these magnetic highways, their motion constrained to follow the curved geometry of field lines that connect different regions of the solar surface. Coronal loops, some large enough to encompass several Earths, pulse with 11-minute oscillations that reflect the acoustic modes of the Sun's interior. These standing wave patterns, generated by pressure waves bouncing between the photosphere and the base of the convection zone, propagate upward and modulate the coronal plasma density with mathematical precision. The asteroid's atoms ride these acoustic waves like surfers on invisible swells of sound that travel through plasma at velocities approaching the local speed of light. The solar wind begins its acceleration in the lower corona, starting as a gentle breeze of charged particles and eventually reaching supersonic velocities that carry solar material beyond the edge of the solar system. Protons and electrons, heated to temperatures where their thermal velocities exceed the sun's escape velocity, stream outward along open magnetic field lines that extend into interplanetary space. The asteroid's hydrogen nuclei join this cosmic river, their destiny now tied to the solar wind's journey toward the heliopause and beyond. Coronal heating mechanisms operate through processes so complex that they require supercomputer simulations to model accurately. Magnetic reconnection events, where oppositely directed field lines approach each other and suddenly snap together, release stored magnetic energy as heat and particle acceleration. These reconnection sites appear throughout the corona as bright points in X-ray images, each one a miniature laboratory where the fundamental physics of plasma behavior plays out on scales ranging from meters to thousands of kilometers. The asteroid's heavier elements, silicon, magnesium, aluminum, become highly charged ions that emit characteristic X-ray lines when their remaining electrons transition between energy levels. These emission lines serve as diagnostic tools for coronal physicists, revealing temperature, density, and magnetic field strength through spectroscopic analysis. The asteroid's brief passage creates temporary enhancements in these spectral signatures, like adding a few drops of food coloring to a vast ocean of plasma. Wave heating represents another candidate mechanism for coronal energy deposition. Alphen waves, magnetohydrodynamic oscillations that travel along magnetic field lines, carry energy from the photosphere's turbulent convection into the corona's tenuous medium. These waves, named after Swedish physicist Hannes Alfvén, propagate at velocities determined by the magnetic field strength and plasma density. As they steepen into shock waves, their kinetic energy converts to thermal energy, heating the coronal plasma to its extreme temperatures. Timescales in the corona span from milliseconds to years, reflecting the diverse range of physical processes operating in this exotic environment. Magnetic reconnection events occur in seconds, while coronal mass ejections develop over hours, and large-scale magnetic structures evolve over the 11-year solar cycle. The asteroid's atoms experience all these timescales simultaneously, their individual trajectories determined by rapid magnetic fluctuations, while their collective behavior follows the slower evolution of large-scale coronal structures. The corona extends far beyond the visible disk of the Sun, stretching millions of kilometers into space as streamers and plumes that follow magnetic field lines. During total solar eclipses, when the Moon blocks the photosphere's overwhelming brightness, the corona becomes visible as a silvery nimbus surrounding the darkened Sun. The asteroid's atoms contribute to this ethereal glow, their Thomson scattering of photospheric light adding imperceptibly to the corona's luminous beauty. Coronal holes, regions where magnetic field lines extend into interplanetary space rather than looping back to the Sun's surface, appear as dark areas in the X-ray images of the corona. These holes serve as the source regions for high-speed solar wind streams that interact with Earth's magnetosphere to create geomagnetic storms and aurora displays. The asteroid's particles that enter coronal holes begin their journey toward the outer solar system, destined to become part of the tenuous medium that fills the space between worlds. The corona's magnetic topology changes continuously as the Sun rotates and its internal magnetic field evolves. Coronal loops brighten and fade, streamers shift position, and new active regions emerge as magnetic flux tubes rise from the solar interior. The asteroid's dispersed atoms serve as tracers for these magnetic changes, their emission signatures recording the dynamic evolution of coronal structures with each spectroscopic observation. Solar energetic particle events, accelerated by magnetic reconnection and shock waves in the corona, can reach energies exceeding those produced by the largest terrestrial particle accelerators. Some of the asteroid's heavier nuclei join these energetic populations, achieving velocities that represent significant fractions of the speed of light. These relativistic particles follow magnetic field lines that spiral outward from the Sun, creating radiation hazards for spacecraft and astronauts venturing beyond Earth's protective magnetosphere. The asteroid's complete ionization in the corona represents the final transformation of matter that began its journey as condensed grains in the early solar nebula, from solid rock to liquid magma to plasma to fully ionized nuclei. The material has experienced every possible state of matter. Only took 4.5 billion years to return home to the furnace that created it. The irony glows softly in X-ray wavelengths, invisible to human eyes but recorded faithfully by instruments designed to study the most extreme environments in the solar system. Coronal physics operates at the intersection of thermodynamics, electromagnetism, and fluid mechanics, creating a complex system where small-scale processes influence large-scale phenomena through nonlinear interactions. The asteroid's atoms become part of this system, their individual motions contributing to collective behaviors that emerge from the statistical mechanics of millions of charged particles interacting through electromagnetic forces across vast ranges of spatial and temporal scales. Below the corona, beneath the chromosphere and photosphere, the asteroid's ionized atoms sink into the convection zone, a vast spherical shell that extends from 70% of the Sun's radius outward to the visible surface. Here, in this realm of churning plasma cells, energy transport shifts from radiation to convection, and the asteroid's constituent particles begin a journey that will carry them through circular currents lasting hundreds of thousands of years. The convection zone operates like a cosmic heat engine, driven by the temperature difference between the nuclear furnace at the Sun's core and the relatively cool photosphere above. Granulation patterns visible on the Sun's surface represent the upper manifestation of convective cells that extend downward for 200,000 kilometers, a distance equivalent to traveling from Earth to the Moon and halfway back again. These cells, ranging in size from a few hundred to several thousand kilometers across, rise and fall in predictable cycles that transport energy upward from the Sun's interior. The asteroid's atoms become entrained in these massive circulation patterns, their upward and downward motions synchronized with plasma flows that dwarf any meteorological phenomenon on Earth. Temperature gradients in the convection zone follow the adiabatic lapse rate, meaning that rising plasma cools at a predictable rate determined by the expansion of gas under decreasing pressure. Descending plasma heats up as it encounters higher pressures in the Sun's depths. This thermodynamic cycle, repeated billions of times across millions of convective cells, creates the mechanical energy that drives mass transport throughout the outer third of the Sun's interior. The asteroid's atoms experience these temperature variations as they ride the convective currents, cycling between regions where temperatures exceed 2 million Kelvin and zones barely hot enough to maintain complete ionization. Plasma physics in the convection zone operates under conditions that challenge theoretical understanding. The Reynolds number, a dimensionless quantity that describes the ratio of inertial forces to viscous forces in fluid flow, reaches values exceeding 1014 in solar convection, making it the most turbulent environment known in the universe. For comparison, the most turbulent flows achievable in terrestrial laboratories reach Reynolds numbers of only 10 or 6. This extreme turbulence creates a cascade of energy, from large-scale convective motions down to microscopic plasma instabilities. The asteroid's heavier elements iron, silicon, magnesium become mixed throughout the convection zone, Through a process that operates like a cosmic blender, convective mixing erases chemical gradients that might have existed in the Sun's outer layers, creating a well-stirred reservoir where element abundances remain uniform from the base of the convection zone to the photosphere. This mixing process explains why spectroscopic observations of the Sun's surface accurately reflect the composition of material in the convection zone's depths. Magnetic field generation occurs throughout the convection zone through a process called the magnetic dynamo. The differential rotation of the Sun, its equator, spins faster than its poles combined with convective motion, stretches and twists magnetic field lines into complex configurations. The asteroid's ionized atoms, being excellent electrical conductors, participate in this dynamo process by carrying electric currents that amplify and maintain the Sun's global magnetic field. These currents, though individually tiny, sum to create magnetic phenomena that influence the entire solar system. Convective turnover times vary with depth and latitude, creating a complex three-dimensional circulation pattern that astronomers are only beginning to understand through helioseismic observations. Near the surface, convective cells complete their circulation in minutes to hours, while deeper cells may require months or years to complete a full cycle. The deepest convective motions, driven by the steepest temperature gradients, operate on timescales approaching 1 million years. The asteroid's atoms will participate in all these circulation patterns, their ultimate fate determined by which convective stream captures them during their descent. Sound waves generated by turbulent convection propagate throughout the Sun's interior, creating the acoustic oscillations that helioseismologists use to probe solar structure. These waves, with periods ranging from minutes to hours, reflect off the Sun's core and travel back to the surface, where they create measurable oscillations in brightness and velocity. The asteroid's dispersal briefly modifies the local density structure, creating subtle changes in the wave propagation that could, in principle, be detected by sufficiently sensitive instruments. The convection zone boundary, located at approximately 70% of the solar radius, marks a fundamental transition in the Sun's energy transport mechanism. Below this boundary, in the radiative zone, energy moves outward primarily through the emission and absorption of photons. Above it, convective currents dominate energy transport. The asteroid's atoms that sink to this boundary encounter a region where the physics of energy transfer shifts dramatically, like crossing from a flowing river into a still lake. Helium settling represents a slow but significant process in the convection zone's chemical evolution. Helium atoms, being more massive than hydrogen, tend to sink gravitationally through the convective medium over timescales of millions of years. This process gradually increases the helium abundance in the Sun's core while decreasing it in the convection zone. The asteroid's contribution of trace helium joins this slow gravitational sorting, its atoms destined to participate in the Sun's long-term compositional evolution. Convective overshoot, a phenomenon where convective motions penetrate slightly beyond the formal boundary of the convection zone, creates a transition layer where both convective and radiative energy transport operate simultaneously. Some of the asteroid's atoms may become trapped in this boundary region, their motion constrained by the changing physics of energy transport. This overshoot layer, only a few % of the solar radius thick, plays a crucial role in determining the Sun's overall structure and evolution. The asteroid's organic compounds, completely dissociated into their constituent atoms, contribute carbon, nitrogen, and oxygen to the convection zone's inventory of heavy elements. These elements, originally formed in the nuclear furnaces of massive stars and expelled in supernova explosions, have travelled through interstellar space for billions of years before condensing into the asteroid that now feeds them back to a stellar environment. The cosmic recycling continues, each atom destined for further adventures in stellar nucleosynthesis. Magneto-hydrodynamic instabilities in the convection zone create small-scale turbulence that operates on spatial scales ranging from kilometers to meters. These instabilities, driven by the interaction between magnetic fields and plasma flows, dissipate energy and contribute to the heating of the solar atmosphere above. The asteroid's conducting atoms participate in these microscopic processes, their collective motion contributing to electric currents that generate magnetic fields and electromagnetic heating. Pressure at the base of the convection zone reaches approximately 10 billion pascals, equivalent to the pressure found 1,000 kilometers beneath Earth's surface. Under these conditions, hydrogen exists in a partially degenerate state where quantum mechanical effects begin to influence the gas properties. The asteroid's hydrogen nuclei, stripped of their electrons in the corona above, experience this exotic matter state as they sink toward the Sun's radiative interior. Temperature stratification in the convection zone follows nearly adiabatic profiles, meaning that entropy remains approximately constant along convective streamlines. This thermodynamic constraint creates a specific relationship between temperature and pressure that determines the convection zone's vertical structure. The asteroid's atoms trace out these adiabatic curves as they rise and fall with the convective currents, their thermodynamic state evolving according to the fundamental laws that govern gas behavior in stellar interiors. The convection zone contains approximately 30% of the Sun's total mass, making it a substantial reservoir for the storage and transport of energy, angular momentum, and chemical elements. The asteroid's contribution to this reservoir remains infinitesimal, yet its atoms will participate in the zone's collective behavior for geological timescales. Some atoms may reach the surface within decades, while others might remain trapped in deep convective cells for hundreds of millennia before eventually rising to contribute their energy to the photosphere's radiant output. Convective energy transport efficiency in the Sun exceeds that of any terrestrial heat engine, achieving energy transfer rates that would require technological systems of impossible complexity to duplicate. The convection zone moves approximately 10 to 26 watts of power from the solar interior to the surface, enough energy to supply human civilization for billions of years. The asteroid's atoms become part of this cosmic power plant, their kinetic and thermal energy contributing to the vast flow of energy that sustains life throughout the solar system. Beneath the convection zone lies the radiative zone, a spherical shell extending from 30% of the Sun's radius outward to the convective boundary above. Here, the asteroid's atoms enter a realm where energy transport operates through an entirely different mechanism: the emission, absorption, and re-emission of photons in an intricate dance that can last hundreds of thousands of years. In this dense medium, where pressures exceed 1 billion Earth atmospheres and temperatures climb toward 15 million Kelvin, light itself becomes trapped in a random walk so complex that photons created at the zone's base take longer to reach the surface than human civilization has existed. The radiative zone's density increases dramatically with depth, rising from roughly 1/10 the density of water at its upper boundary to nearly 10 times water's density at its base near the solar core. Under these extreme conditions, matter exists in a state unknown anywhere else in the solar system, a fully ionized plasma so dense that quantum mechanical effects begin to influence the behavior of particles. The asteroid's atoms, now completely stripped of electrons, navigate this environment as bare nuclei surrounded by a sea of free electrons that move according to the statistical laws of degenerate matter. Photon diffusion in the radiative zone operates through a process that physicists describe as a drunkard's walk. Each photon travels only a few millimeters before encountering an electron or ion that absorbs it and immediately re-emits it in a random direction. This absorption and re-emission cycle repeats billions of times as each photon slowly works its way outward through the dense plasma. The asteroid's atoms participate in this process both as absorbers and emitters, their nuclei occasionally capturing photons and releasing them at slightly different energies, determined by quantum mechanical selection rules. Opacity. The measure of how effectively matter absorbs electromagnetic radiation varies throughout the radiative zone according to temperature, density, and composition. Heavier elements like the iron and silicon from the asteroid contribute disproportionately to the zone's opacity, despite their relatively low abundance. These elements possess numerous electron energy levels that can absorb photons across a wide range of wavelengths, making them particularly effective at trapping light. The asteroid's heavy element content, though infinitesimal compared to the zone's total mass, joins the Sun's existing inventory of opacity sources. Temperature gradients in the radiative zone follow a precise mathematical relationship determined by the balance between energy generation in the core and energy transport toward the surface. This gradient, steeper than the adiabatic lapse rate that governs convection, creates the thermodynamic conditions necessary for radiative energy transport to dominate over convective mixing. The asteroid's atoms experience these temperature variations as they diffuse slowly through the zone, their thermal energy increasing as they sink toward the hotter depths below. Magnetic fields in the radiative zone remain largely trapped and isolated from the dynamic magnetic phenomena occurring in the convection zone above, without convective motions to stretch and amplify field lines. Magnetic structures in the radiative zone evolve slowly, primarily through the process of magnetic diffusion. The asteroid's conducting atoms carry tiny electric currents that contribute to these fossil magnetic fields, preserving remnants of the Sun's primordial magnetic structure from the era of stellar formation. Nuclear burning occurs exclusively at the base of the radiative zone and in the core below, where temperatures exceed the threshold required for hydrogen fusion into helium. The asteroid's hydrogen nuclei that sink to these depths join the proton-proton chain reaction that powers the Sun's luminosity. These fusion reactions release gamma-ray photons with energies millions of times higher than visible light, beginning their long journey toward the surface through the radiative zone's labyrinthine path of absorption and re-emission. Hydrostatic equilibrium maintains the radiative zone's structural stability through the precise balance between gravitational compression and radiation pressure. Each layer of the zone supports the weight of all layers above it, through the pressure generated by trapped photons and thermal motion of particles. The asteroid's atoms contribute negligibly to this pressure balance, yet they experience its effects as they settle into gravitational equilibrium within the dense plasma medium. Helium accumulation in the radiative zone occurs gradually as the products of nuclear fusion diffuse outward from the core, unlike the convection zone above, where mixing homogenizes composition. The radiative zone preserves compositional gradients that reflect the history of nuclear burning and element transport. The asteroid's helium content merges with these existing gradients, its atoms destined to participate in the slow evolution of the Sun's internal structure over billion-year timescales. The zone's thermal structure exhibits remarkable stability, with temperature profiles that have remained essentially unchanged for billions of years. This thermal equilibrium results from the fundamental physics of radiative energy transport, which automatically adjusts to maintain the precise temperature gradient required for steady energy flow, the asteroid's brief thermal perturbation dissipates quickly into the zone's vast thermal reservoir, leaving no lasting signature in the Sun's internal temperature distribution. Quantum mechanics becomes increasingly important in the radiative zone's deeper regions, where electron degeneracy pressure contributes significantly to the total pressure support. Under these conditions, electrons behave according to Fermi-Dirac statistics rather than classical Maxwell-Boltzmann distributions. The asteroid's electrons, stripped away in the corona above, join this quantum mechanical electron gas that fills the spaces between nuclei throughout the radiative zone. Neutrino production in the nuclear reactions at the zone's base creates a constant flux of nearly massless particles that escape the Sun immediately, carrying away a small fraction of the nuclear energy without interacting with the dense plasma. Unlike photons, which require hundreds of thousands of years to diffuse outward, neutrinos travel at the speed of light and reach Earth's surface just 8 minutes after their creation in the solar core. The asteroid's hydrogen nuclei that undergo fusion contribute to this neutrino flux, their nuclear reactions adding to the stream of particles that pass through Earth every second. Chemical diffusion operates slowly in the radiative zone, gradually separating elements according to their mass and ionization state. Heavier elements tend to settle gravitationally while lighter elements diffuse upward, creating subtle composition gradients that evolve over stellar lifetimes. The asteroid's diverse elemental inventory from lithium to iron participates in this cosmic sorting process, each element finding its equilibrium distribution within the zone's gravitational and thermal environment. Pressure ionization maintains the complete dissociation of all atoms throughout the radiative zone, despite temperatures that would allow partial recombination under lower pressure conditions. The extreme pressure compresses electron orbitals to the point where bound states become energetically unfavorable, ensuring that all matter exists as a plasma of free nuclei and electrons. The asteroid's atoms remain completely ionized throughout their residence in this zone, their electronic structure reduced to bare nuclear charges. Convective instability boundaries mark the transitions where the temperature gradient becomes steep enough to trigger convective overturning. The asteroid's atoms that approach these boundaries may become entrained in small-scale convective cells that transport them rapidly upward or downward, dramatically altering their journey through the solar interior. These boundary layers, though thin compared to the radiative zone's total thickness, play crucial roles in determining the overall structure of the Sun's interior. Radiative acceleration affects different elements unequally, with the radiation pressure on heavier elements sometimes exceeding gravitational forces. This phenomenon can drive selective mass loss and element separation in stellar atmospheres, though in the Sun's case, the effects remain subtle. The asteroid's iron and silicon nuclei experience slightly different radiative forces than hydrogen and helium, contributing to microscopic element separation processes that operate over million-year timescales. The radiative zone serves as the Sun's primary energy storage reservoir, containing thermal energy equivalent to the star's total luminous output for several million years. The asteroid's atoms become part of this energy bank, their thermal and kinetic energy contributing to the reservoir that buffers the Sun's output against variations in nuclear energy generation. This thermal inertia explains why the Sun's luminosity remains remarkably stable, despite the chaotic nature of nuclear fusion reactions in the core below. Stellar evolution models predict that the radiative zone will gradually shrink as the Sun ages, and its core accumulates helium ash from hydrogen burning. Over the next several billion years, the convection zone above will deepen as the Sun evolves toward its red giant phase. The asteroid's atoms will experience this slow evolution, their environment changing imperceptibly as the Sun's internal structure adjusts to the long-term consequences of nuclear energy generation. At the base of the radiative zone, where temperatures exceed 15 million Kelvin and pressures reach 100 billion Earth atmospheres, the asteroid's hydrogen nuclei encounter the nuclear furnace that powers the Sun. Here, in the core region, extending from the center to approximately 25% of the solar radius, the fundamental forces of nature overcome the electromagnetic repulsion between positively charged protons and allow nuclear fusion to proceed. The asteroid's hydrogen atoms, stripped of their electrons eons ago in the corona, now exist as bare protons moving at velocities approaching 300 kilometers per second through a plasma so dense that matter approaches the consistency of liquid mercury. The proton-proton chain reaction begins when two hydrogen nuclei collide with sufficient energy to overcome the Coulomb barrier, the electromagnetic force that normally keeps positively charged particles apart. Quantum tunneling allows this fusion to occur at energies lower than classical physics would predict, enabling nuclear reactions at the relatively modest temperatures found in stellar cores. One of the colliding protons transforms into a neutron through beta plus decay, releasing a positron and a neutrino while forming deuterium, the heavy isotope of hydrogen. The asteroid's protons join this nuclear lottery, where only one collision in 10 billion results in successful fusion. Deuterium nuclei, once formed, quickly encounter additional protons in the dense core plasma. This second fusion reaction proceeds much more rapidly than the initial proton-proton collision, creating helium-3 nuclei and releasing gamma-ray photons with energies of several million electron volts. These high-energy photons begin their long journey toward the Sun's surface, destined for hundreds of thousands of years of random scattering through the radiative zone above. The asteroid's hydrogen contribution to these reactions represents an infinitesimal fraction of the Sun's total fusion rate. Yet each successful fusion event releases energy equivalent to burning several tons of coal. The final step in the proton-proton chain occurs when two helium-3 nuclei collide and fuse, producing helium-4 and releasing two protons back into the core plasma. This reaction completes the nuclear cycle that converts 4 hydrogen nuclei into one helium nucleus, with the mass difference appearing as pure energy according to Einstein's famous equation E=mc2. The released energy, approximately 26 million electron volts per helium nucleus created, powers the Sun's luminosity and creates the radiation pressure that prevents gravitational collapse of the stellar core. Nuclear reaction rates in the solar core depend sensitively on temperature, with fusion rates proportional to approximately the 15th power of the core temperature. This steep temperature dependence creates a natural thermostat that regulates the Sun's energy output if the core heats up slightly. Fusion rates increase dramatically, producing more energy and radiation pressure that causes the core to expand and cool. This negative feedback mechanism has maintained the Sun's stable luminosity for over 4 billion years, despite the chaotic nature of individual nuclear reactions. Helium ash accumulates gradually in the solar core as the ongoing fusion reactions convert approximately 600 million tons of hydrogen into helium every second. This helium, being heavier than hydrogen, cannot undergo further fusion under current core conditions and instead settles gravitationally toward the center of the Sun. The asteroid's hydrogen nuclei that successfully fuse join this growing helium reservoir, their nuclear binding energy having been converted to the gamma rays and neutrinos that carry energy away from fusion sites. Neutrino production accompanies each step of the proton-proton chain, creating nearly massless particles that escape the Sun immediately without further interaction. These neutrino produced at a rate of approximately 1038 per second, carry away roughly 2% of the nuclear energy and provide astronomers with a direct window into the solar core's current fusion activity. Some neutrinos originate from the asteroid's hydrogen nuclei, their detection on Earth offering proof that the asteroid's atoms have successfully joined the Sun's nuclear burning process. Core convection operates on a much smaller scale than the outer convection zone, extending only to approximately 25% of the solar radius. This inner convective region mixes the helium ash produced by fusion with the remaining hydrogen fuel, preventing the accumulation of composition gradients that would alter the nuclear burning rate. The asteroid's fusion products participate in this mixing process, their helium nuclei distributed throughout the convective core by fluid motions driven by the energy release from nuclear reactions. Stellar nucleosynthesis beyond hydrogen burning remains impossible under current solar core conditions. The fusion of helium into heavier elements requires temperatures exceeding 100 million Kelvin, far higher than the Sun's current core temperature of 15 million Kelvin. The asteroid's heavier elements, carbon, oxygen, silicon, iron, remain unchanged by their passage through the nuclear furnace, serving as passive witnesses to the hydrogen fusion occurring around them. These elements await the Sun's eventual evolution into a red giant, when core temperatures may rise sufficiently to trigger helium burning. Quantum mechanical effects dominate nuclear reaction probabilities in the solar core, where particle energies remain well below the classical threshold for overcoming electromagnetic repulsion. The wave nature of protons allows them to tunnel through the Coulomb barrier with probabilities that depend exponentially on their kinetic energy. The asteroid's protons experience these quantum effects directly, their fusion success determined by probability distributions that reflect the fundamental uncertainty principle governing atomic scale interactions. Gravitational contraction provides the ultimate energy source that maintains the core's nuclear burning temperature. As the Sun slowly converts hydrogen to helium, the mean molecular weight of the core increases, causing gradual gravitational contraction that releases potential energy as heat. This Kelvin-Helmholtz contraction, operating over billion-year timescales, slowly increases the core temperature and fusion rate, causing the Sun's luminosity to brighten gradually throughout its main sequence lifetime. Radiation pressure from the intense gamma-ray flux generated by nuclear fusion creates a significant contribution to the total pressure that supports the solar core against gravitational collapse. These high-energy photons, trapped by the dense plasma surrounding the nuclear burning region, exert forces that help maintain hydrostatic equilibrium in the deepest regions of the Sun. The asteroid's contribution to this radiation field remains negligible, yet its atoms experience the immense radiation pressure that prevents stellar core collapse. Magnetic fields in the solar core remain largely fossil remnants from the Sun's formation, preserved in the dense plasma where magnetic diffusion operates slowly compared to stellar evolution timescales. These primordial magnetic fields may influence the rate of nuclear reactions through subtle effects on charged particle trajectories, though current models suggest such influences remain small compared to thermal and density effects. The asteroid's charged nuclei move through these ancient magnetic fields, their paths occasionally deflected by electromagnetic forces that date to the solar system's birth. Energy transport in the core occurs primarily through radiation, with gamma rays and X-rays carrying nuclear energy outward toward the radiative zone boundary. Convective transport becomes significant only in regions where nuclear energy generation creates steep temperature gradients that exceed the adiabatic limit for stable stratification. The asteroid's atoms participate in both transport mechanisms, contributing to radiative opacity when they absorb and re-emit photons and joining convective flows when local heating drives fluid instabilities. Core evolution proceeds imperceptibly on human timescales, with structural changes occurring over millions to billions of years as nuclear burning gradually alters the core's composition and temperature structure. Helioseismic observations provide evidence for these slow changes through measurements of acoustic wave frequencies that probe the core's density and sound speed profiles. The asteroid's atoms will experience this evolutionary process throughout their residence in the solar core, witnessing the gradual transformation that will eventually lead to the Sun's red giant phase. The solar core represents the most extreme environment in the solar system, where matter exists under conditions that compress atomic nuclei to densities approaching those found in neutron stars. Here, the asteroid's journey through increasingly exotic states of matter reaches its culmination from solid rock to liquid magma, to plasma, to fully ionized gas, to nuclear fuel, burning in the cosmic furnace that has sustained life on Earth for billions of years. Only took 4.5 billion years for these atoms to complete their return journey to the stellar environment where they were originally forged. The asteroid's metallic components, iron, nickel, cobalt, and trace amounts of precious metals carry with them a property that distinguishes them from the Sun's lighter elements: significant magnetic susceptibility. As these heavy nuclei disperse throughout the solar interior and eventually work their way back toward the surface, they interact with the Sun's magnetic field in ways that create temporary perturbations in the delicate electromagnetic architecture that governs solar activity. The Sun's magnetic field, generated by the complex interplay of rotation and convection in a process known as the solar dynamo, responds to these foreign magnetic influences with a sensitivity that reflects the nonlinear nature of magnetohydrodynamic systems. Iron nuclei, stripped of all 26 electrons in the corona's extreme environment, retain their nuclear magnetic moments, tiny magnetic dipoles that align with or against external magnetic fields, depending on their quantum mechanical spin states. As these iron nuclei circulate through the convection zone's turbulent plasma, they contribute microscopic magnetic perturbations that propagate through the conducting medium according to the laws of electromagnetic induction. These perturbations, though individually negligible, can trigger cascade effects in a system already poised on the edge of magnetic instability. The solar dynamo operates through the stretching and twisting of magnetic field lines by differential rotation and convective motion. The Sun's equator rotates once every 25 days, while the polar regions require 35 days to complete a rotation, creating shear flows that win magnetic field lines into complex helical configurations. The asteroid's conducting materials become part of this dynamo process, their motion through existing magnetic fields generating electric currents that either amplify or suppress the field depending on their direction relative to the background magnetic structure. Magnetic flux tubes, rope-like structures of concentrated magnetic field, rise from the solar interior to the surface carrying magnetic energy generated by dynamo action. These flux tubes, typically several hundred kilometers in diameter, maintain their coherence through magnetic tension that acts like elastic bands under stress. The asteroid's metallic content, distributed along these flux tubes as they rise through the convection zone, modifies the tube's magnetic properties and influences their buoyancy as they approach the photosphere. Solar active regions form where magnetic flux tubes emerge through the photosphere and create the complex field configurations that produce sunspots, solar flares, and coronal mass ejections. The asteroid's iron content, having joined the circulation patterns that transport magnetic flux from the solar interior, contributes to the heavy element abundance in these active regions. Spectroscopic observations of sunspots reveal enhanced concentrations of iron and other metals, reflecting the transport of dynamo-generated magnetic fields and their associated metallic traces from the convection zone depths. Sunspot formation occurs when strong magnetic fields suppress convection in localized regions of the photosphere, creating areas of reduced temperature that appear dark against the surrounding solar surface. The magnetic field strengths in sunspot umbrae reach several thousand Gauss, powerful enough to levitate a paperclip if such fields existed on Earth. The asteroid's metallic atoms, trapped within these magnetic structures, experience forces that exceed gravitational acceleration as they follow the twisted geometry of sunspot magnetic fields. Magnetic reconnection events in solar active regions release stored magnetic energy through a process that remains incompletely understood despite decades of theoretical and observational study. When oppositely directed magnetic field lines approach each other, they can suddenly snap together and reorganize into lower energy configurations, converting magnetic energy into kinetic energy of charged particles and electromagnetic radiation. The asteroid's conducting atoms participate in these reconnection events, their motion through the reconfiguring magnetic fields contributing to the electric currents that facilitate energy release. Solar flares represent the most violent explosions in the solar system, releasing energies equivalent to billions of hydrogen bombs within minutes or hours. These events occur when magnetic reconnection destabilizes complex field configurations in solar active regions, accelerating particles to relativistic velocities and heating plasma to temperatures exceeding 10 million Kelvin. The asteroid's atoms caught in flare-producing active regions experience these extreme conditions. Their thermal and kinetic energies increase dramatically by the magnetic energy release. The 11-year solar cycle reflects the periodic reversal of the Sun's global magnetic field, driven by the dynamo process operating in the convection zone. During solar maximum, magnetic activity reaches peak levels with numerous sunspots, flares, and coronal mass ejections. The asteroid's metallic content, distributed throughout the convection zone by this time, participates in the dynamo process that generates each successive solar cycle. Its atoms serve as magnetic tracers for the slow evolution of the Sun's large-scale magnetic field over decade-long time periods. Coronal mass ejections launch billions of tons of magnetized plasma into interplanetary space at velocities exceeding 1,000 kilometers per second. These events occur when magnetic field lines in the corona become so twisted and stressed that they snap and propel large volumes of solar material away from the Sun. The asteroid's atoms, if present in the magnetic structures that produce coronal mass ejections, begin interplanetary journeys that may carry them beyond the orbit of Mars before the solar wind disperses them throughout the heliosphere. Magnetic helicity, a measure of the twist and linkage in magnetic field configurations, accumulates in solar active regions as convective motions and differential rotation stress the magnetic field lines. This helicity must be removed from the solar atmosphere to prevent the indefinite buildup of magnetic stress, and coronal mass ejections serve as the primary mechanism for helicity removal. The asteroid's conducting atoms contribute infinitesimally to the transport of magnetic helicity from the solar interior to interplanetary space. Helioseismic observations reveal that magnetic fields alter the propagation of acoustic waves through the solar interior, creating signatures that allow astronomers to map subsurface magnetic structures. The asteroid's metallic content, by modifying local magnetic field strengths and configurations, contributes to these helioseismic signals, in ways that could theoretically be detected by sufficiently sensitive instruments. These observations provide evidence for the deep connections between magnetic activity and the Sun's internal structure. Magneto-hydrodynamic waves propagate through the solar atmosphere, carrying energy from magnetic disturbances in the photosphere to the corona above. These waves, traveling along magnetic field lines at the Alphen velocity, transport magnetic stress and energy across vast distances within the solar atmosphere. The asteroid's atoms, constrained to follow magnetic field lines in the ionized solar plasma, ride these magneto-hydrodynamic waves as they carry energy and information throughout the Sun's magnetic environment. Solar magnetic fields exhibit fractal properties, with complex structures appearing at all observable scales from granular to global. This self-similar organization reflects the turbulent nature of the magneto-hydrodynamic processes that generate and maintain solar magnetism. The asteroid's metallic atoms experience this fractal magnetic environment directly, their trajectories determined by field line configurations that display complexity across multiple spatial and temporal scales. Magnetic flux conservation requires that the total magnetic flux threading any closed surface remain constant unless external forces act to change it. In the solar context, this conservation law constrains how magnetic field lines can move and reorganize as they respond to plasma motions and magnetic instabilities. The asteroid's conducting atoms, by carrying electric currents that generate magnetic fields, participate in the complex feedback processes that maintain magnetic flux conservation throughout the solar atmosphere. The solar magnetic field extends far beyond the visible surface, creating the heliospheric magnetic field that influences charged particle propagation throughout the solar system. This field, embedded in the solar wind plasma, rotates with the Sun and creates a spiral pattern known as the Parker spiral that guides energetic particles along predictable trajectories. The asteroid's atoms that escape the solar atmosphere through coronal mass ejections or solar wind acceleration follow these magnetic highways toward the outer reaches of the solar system. Space weather phenomena, geomagnetic storms, radiation storms, and radio blackouts result from the interaction between solar magnetic disturbances and Earth's magnetosphere. The asteroid's contribution to solar magnetic activity, though infinitesimal, joins the complex chain of cause and effect that connects events in the solar interior to technological impacts on human civilization. Modern society's dependence on satellite communications, GPS navigation, and electrical power grids creates vulnerabilities to space weather that trace their origins to magnetic processes operating in the Sun's depths. Magnetic field emergence through the photosphere creates the complex active region structures that dominate solar magnetic activity. This emergence process, driven by magnetic buoyancy and modified by convective flows, determines the spatial and temporal patterns of solar magnetic phenomena. The asteroid's metallic atoms, carried upward by rising magnetic flux tubes, witness the birth of active regions as magnetic fields break through the solar surface and create the configurations that will eventually produce flares, prominences, and coronal mass ejections. The asteroid's dissolution creates pressure waves that propagate through the Sun's interior as heliosysmic oscillations, acoustic vibrations that transform the star into a cosmic musical instrument, resonating with frequencies determined by its internal structure. These sound waves, generated by the sudden deposition of kinetic energy when the rocky mass encountered the photosphere, travel through the solar plasma at velocities approaching the local speed of sound, creating ripples that carry information about the Sun's temperature, density, and composition from its surface to its core and back again. Heliosysmology, The study of these stellar oscillations allows astronomers to probe the Sun's interior with a precision that rivals the seismic imaging techniques used to explore Earth's deep structure. Acoustic waves in the solar interior exhibit characteristics fundamentally different from sound waves in terrestrial environments. The temperature-dependent speed of sound in the Sun's plasma increases from approximately 7 km per second at the photosphere to over 500 km per second in the nuclear burning core. This velocity structure creates acoustic waveguides that trap certain frequencies while allowing others to propagate freely, resulting in standing wave patterns that give the Sun its characteristic oscillation modes. The asteroid's impact contributes brief perturbations to these standing waves, like striking a bell and listening to its resonant frequencies. Global oscillation modes of the Sun involve coherent motions of vast regions of the stellar interior, with some modes causing the entire solar surface to expand and contract with periods of approximately 5 minutes. These breathing modes, discovered through precise measurements of Doppler shifts in solar spectral lines, reveal the Sun's fundamental acoustic properties with remarkable accuracy. The asteroid's energy input briefly excites additional oscillation modes, creating temporary enhancements in the helioseismic spectrum that decay over periods of hours to days as the acoustic energy dissipates through radiative damping. Pressure waves generated by the asteroid's dissolution travel radially inward through the convection zone, experiencing refraction and reflection as they encounter regions of varying sound speed and density. The waves that reach the solar core undergo total internal reflection, bouncing off the acoustic boundary created by the dramatic density increase at the core's edge. These reflected waves return to the surface carrying information about the core's structure, encoded in their travel times and phase relationships. The asteroid's seismic signature thus provides a brief snapshot of conditions throughout the entire solar interior. Mode conversion occurs when acoustic waves encounter magnetic field concentrations in the solar atmosphere, transforming some of the acoustic energy into magnetohydrodynamic waves that propagate along field lines rather than in all directions. This conversion process, analogous to the transformation of seismic waves at discontinuities in Earth's interior, creates complex wave interference patterns that modify the helioseismic spectrum. The asteroid's impact location and the local magnetic field configuration determine how much acoustic energy undergoes conversion to magnetic wave modes. Frequency splitting in solar oscillations reveals the effects of rotation, magnetic fields, and a spherical structure on the Sun's acoustic properties. Each oscillation mode exhibits a characteristic frequency that splits into multiple components when perturbations break the spherical symmetry that would characterize a perfectly uniform, non-rotating star. The asteroid's contribution to this frequency splitting remains undetectable with current instruments, yet it represents a genuine physical perturbation that influences the Sun's oscillatory behavior according to the same principles that govern planetary seismology. Wave absorption and scattering in the solar interior cause acoustic modes to decay over time, scales ranging from days to weeks, depending on their frequency and spatial structure. High-frequency modes, corresponding to waves with short wavelengths, experience stronger damping due to increased interactions with turbulent convection and radiative processes. The asteroid's seismic energy undergoes this same damping, its acoustic signature gradually fading as wave energy converts to heat and electromagnetic radiation through plasma physics processes operating throughout the solar interior. Helioseismic tomography reconstructs three-dimensional images of the solar interior by analyzing the travel times of acoustic waves along different ray paths through the Sun's volume. This technique, similar to medical CT scans but applied to stellar structure, reveals details of convective flow patterns, magnetic field configurations, and compositional variations within the Sun. The asteroid's brief seismic contribution could theoretically be incorporated into such tomographic analyses, though its signal remains far below current detection thresholds. Sunspot seismology studies how magnetic fields in active regions modify the propagation of acoustic waves through the solar atmosphere. Sunspots act as acoustic absorbers, converting wave energy into magnetic oscillations that heat the chromosphere and corona above. The asteroid's atoms, if incorporated into magnetic flux tubes that eventually emerge as sunspots, contribute to these seismic magnetic interactions that link helioseismic observations to solar magnetic activity cycles. Temporal variations in helioseismic frequencies track changes in the Sun's internal structure over timescales ranging from the solar rotation period to the 11-year magnetic activity cycle. These frequency shifts, measured with precisions of parts per million, reveal how magnetic fields, meridional circulation, and thermal structure evolve within the solar interior. The asteroid's impact represents a punctual perturbation in this slowly evolving seismic background, its signature potentially detectable in high-cadence helioseismic data as a brief frequency anomaly. Acoustic ray paths through the solar interior follow complex trajectories determined by the radial variation of sound speed and the effects of solar rotation. Waves traveling in the direction of rotation experience Doppler shifts that differ from those traveling against rotation, creating asymmetries in the oscillation spectrum that reveal the Sun's internal rotation profile. The asteroid's seismic waves participate in this rotational splitting, their frequencies modified by the solar rotation in proportion to their horizontal wavelengths and propagation directions. Deep focus helioseismology uses acoustic waves that penetrate to the solar core to study nuclear burning processes and the accumulation of helium ash from hydrogen fusion. These waves, with periods longer than 30 minutes, can probe the core's density and sound speed with sufficient precision to detect the gradual structural changes associated with stellar evolution. The asteroid's seismic contribution includes components at these long periods, though their amplitudes remain negligible compared to the natural background of solar oscillations driven by convective turbulence. Local helioseismology techniques analyze wave propagation in small regions of the solar surface to map subsurface structures with spatial resolutions of a few thousand kilometers. These methods reveal convective flow patterns, emerging magnetic flux tubes, and thermal anomalies in the near-surface layers where most acoustic wave energy concentrates. The asteroid's impact site could theoretically be studied using these local techniques, though the seismic signature would likely be overwhelmed by the natural turbulence of solar convection. Neutrino helioseismology represents an emerging field that combines neutrino astronomy with acoustic wave studies to probe the solar core's nuclear burning processes in real time. Unlike acoustic waves, which require hundreds of thousands of years to carry information from the core to the surface, neutrinos escape the Sun immediately and provide instantaneous information about nuclear reaction rates. The asteroid's hydrogen nuclei that undergo fusion contribute to the neutrino flux, their nuclear reactions adding infinitesimally to the stream of particles detected by terrestrial neutrino observatories. Computational helioseismology employs sophisticated numerical models to predict and interpret solar oscillations, incorporating detailed physics of radiative transfer, convection, and magnetic field interactions. These models, running on the world's largest supercomputers, simulate the propagation of acoustic waves through realistic three-dimensional solar structures that include turbulent convection and magnetic field concentrations. The asteroid's seismic signature could be modeled using these computational tools, providing theoretical predictions for comparison with observational data. Astroseismology extends helioseismic techniques to other stars, using stellar oscillations to probe the internal structure of distant suns throughout the galaxy. Space missions dedicated to astroseismology have detected acoustic oscillations in thousands of stars, revealing the diversity of stellar interiors and the universal nature of acoustic wave phenomena. The asteroid's interaction with our Sun represents a microscopic example of the accretion processes that occur throughout stellar evolution, contributing mass and metals to stars as they capture interstellar and interplanetary material. Gravitational wave signatures from solar oscillations remain below current detection thresholds, but represent a theoretical possibility for future gravitational wave observatories with enhanced sensitivity. Large-amplitude helioseismic modes could generate space-time curvature fluctuations that propagate at the speed of light, carrying information about solar structure encoded in gravitational rather than electromagnetic radiation. The asteroid's seismic contribution would produce gravitational waves at frequencies corresponding to its acoustic oscillation spectrum. Though these signals would require gravitational wave detectors millions of times more sensitive than current instruments, solar seismology continues to advance through improved observational techniques, theoretical developments, and computational capabilities that enable ever more detailed studies of stellar interiors. The asteroid's helioseismic signature, though undetectable with present technology, represents a genuine physical process that illustrates the fundamental connections between mechanical disturbances and acoustic wave generation in stellar environments. Each impact event, no matter how small, contributes to the complex symphony of oscillations that allows astronomers to probe the hidden interior of our nearest star. The asteroid's atoms, now completely ionized and distributed throughout the solar atmosphere, join the perpetual outflow of charged particles known as the solar wind, a stream of plasma that flows continuously from the Sun's corona into interplanetary space, at velocities exceeding 400 kilometers per second. This cosmic river carries approximately 1 million tons of solar material into space every second, transporting not only hydrogen and helium nuclei, but also the heavier elements that trace their origins to stellar nucleosynthesis in previous generations of stars. The asteroid's contribution to this mass loss remains infinitesimal compared to the Sun's total output, yet its atoms become part of a process that has been sculpting the solar system's environment for over 4 billion years. Solar wind acceleration occurs through mechanisms that remain partially mysterious, despite decades of spacecraft observations and theoretical modeling. The corona's extreme temperature of 2 million Kelvin provides more than enough thermal energy to drive plasma expansion, yet simple thermal models fail to explain the wind's observed velocities and temperature structure. Magnetic field interactions, wave heating, and magnetic reconnection events all contribute to the acceleration process, creating a complex magneto-hydrodynamic phenomenon that transforms the Sun's hot corona into a supersonic plasma flow that fills the entire heliosphere. Two distinct types of solar wind emerge from different regions of the corona, each carrying characteristic signatures of their source regions. Fast wind, with velocities approaching 800 kilometers per second, originates from coronal holes regions where magnetic field lines extend into interplanetary space rather than forming closed loops that return to the solar surface. Slow wind, moving at roughly half the speed of fast wind, emerges from the boundaries of coronal streamers and carries enhanced abundances of heavy elements that reflect the complex magnetic processes operating in these regions. The asteroid's atoms join both wind types depending on which coronal structures capture them during their passage through the solar atmosphere. Magnetic field lines embedded in the solar wind plasma create the interplanetary magnetic field, a vast network of invisible highways that guide charged particle motion throughout the solar system. The sun's rotation drags these field lines into a spiral configuration known as the Parker spiral, named after physicist Eugene Parker, who first predicted the solar wind's existence in the 1950s. The asteroid's ionized atoms follow these magnetic field lines as they stream away from the sun. Their trajectories constrained by electromagnetic forces that prevent free motion across field lines while allowing rapid transport along them. Composition measurements by spacecraft instruments reveal that the solar wind carries a record of nuclear processes operating in the sun's interior, with isotopic ratios that reflect billions of years of hydrogen fusion and stellar evolution. Heavy elements like iron, silicon, and magnesium appear in the wind with abundances that match spectroscopic observations of the solar photosphere, confirming that the wind samples material from the sun's outer convection zone. The asteroid's diverse elemental inventory merges with this existing composition, its atoms becoming indistinguishable from solar material as they join the outflowing plasma stream. Charge state distributions of heavy ions in the solar wind provide diagnostic information about the temperature and density conditions in their source regions within the corona. Highly charged ions, stripped of most or all of their electrons, indicate passage through regions of extreme temperature where collision rates are sufficient to maintain ionization equilibrium. The asteroid's iron nuclei, already completely ionized in the corona, maintain their +126 charge state as they accelerate into interplanetary space, serving as tracers for the coronal heating processes that drove their ionization. Solar wind variability spans timescales from seconds to decades, reflecting the dynamic nature of the solar magnetic field and its influence on coronal plasma properties. High-speed streams associated with coronal holes create compression regions when they overtake slower wind ahead of them, generating shock waves that accelerate particles and enhance magnetic field strengths. The asteroid's atoms experience these shock acceleration processes, their energies occasionally boosted to levels that qualify them as solar energetic particles, capable of penetrating planetary magnetospheres and reaching planetary surfaces. Turbulence in the solar wind develops as different speed streams interact, and magnetic field irregularities cascade energy from large to small spatial scales. This turbulent cascade, analogous to atmospheric turbulence but operating in a collisionless plasma environment, dissipates magnetic energy and heats the wind as it expands through the solar system. The asteroid's atoms participate in these turbulent processes, their motion influenced by magnetic field fluctuations that operate across spatial scales, ranging from the size of Earth's orbit down to individual particle gyroradii. Coronal mass ejections represent dramatic departures from the steady solar wind flow, launching billions of tons of magnetized plasma into interplanetary space at velocities that can exceed 2,000 kilometers per second. These events, triggered by magnetic instabilities in solar active regions, carry enhanced abundances of heavy elements and can drive powerful shock waves that accelerate particles to relativistic energies. The asteroid's atoms caught in coronal mass ejection source regions experience these explosive acceleration processes, their subsequent interplanetary journey dramatically different from atoms carried by the ambient solar wind. Magnetic reconnection in the solar wind occurs when oppositely directed magnetic field lines encounter each other and suddenly snap together, releasing stored magnetic energy as particle acceleration and plasma heating. These reconnection events, observed by spacecraft throughout the heliosphere, represent fundamental plasma physics processes that operate on scales ranging from Earth's magnetosphere to galactic magnetic fields. The asteroids conducting atoms facilitate these reconnection processes by carrying the electric currents necessary to reconfigure magnetic field topologies. Solar-wind interaction with planetary magnetospheres creates some of the most spectacular phenomena in the solar system, from Earth's aurora displays to the erosion of Mars' ancient atmosphere. When the solar wind encounters a planetary magnetic field, complex boundary layers form where solar plasma and planetary plasma mix through processes involving magnetic reconnection, wave-particle interactions, and plasma instabilities. The asteroid's atoms that reach Earth's magnetosphere may contribute to aurora formation as they precipitate into the upper atmosphere and excite atmospheric gases to emit characteristic colors. Heliosphere boundaries mark the regions where the solar wind encounters the interstellar medium, the tenuous gas and dust that fills the space between stars. The heliopause, located approximately 100 astronomical units from the Sun, represents the boundary where solar wind pressure balances interstellar pressure. Beyond this boundary, the asteroid's atoms join the local interstellar medium, their solar system origins preserved only in their isotopic signatures that record their passage through the Sun's nuclear furnace. Solar wind flux measurements reveal long-term variations that correlate with the 11-year solar magnetic activity cycle, demonstrating the connection between internal solar processes and interplanetary conditions. During solar maximum, enhanced magnetic activity increases the solar wind's heavy element content and drives more frequent coronal mass ejections. The asteroid's atoms dispersed during different phases of the solar cycle carry signatures of the magnetic processes that dominated their acceleration, providing traces for solar activity levels extending back through geological time. Pickup ions form when neutral atoms from interstellar space or cometary outgassing become ionized by solar radiation and are subsequently accelerated by the solar wind's electric and magnetic fields. These newly created ions, picked up by the flowing plasma, contribute to solar wind heating and create distinctive velocity distributions that spacecraft instruments can detect and analyze. Some of the asteroid's atoms may undergo similar pickup processes if they neutralize through charge exchange reactions and are subsequently reionized during their interplanetary journey. Solar wind modeling employs sophisticated magnetohydrodynamic simulations that track plasma flow from the solar corona to the edge of the heliosphere, incorporating effects of magnetic field evolution, turbulent heating, and shock acceleration. These models, constrained by spacecraft observations throughout the solar system, predict solar wind properties at locations far from Earth and help interpret measurements made by interplanetary probes. The asteroid's contribution to these models remains negligible, yet its atoms experience all the physical processes that the models attempt to describe. Termination shock acceleration occurs where the solar wind encounters the interstellar medium and undergoes compression that can accelerate particles to cosmic ray energies. This process, operating at the boundary of the heliosphere, represents one mechanism for generating the galactic cosmic rays that continuously bombard planetary surfaces throughout the solar system. The asteroid's atoms that reach the termination shock may undergo this acceleration, their energies boosted sufficiently to escape the solar system entirely and join the population of interstellar cosmic rays. Solar wind paleontology attempts to reconstruct the history of solar mass loss and magnetic activity through the analysis of solar wind particles implanted in lunar soils, meteorites, and other airless bodies throughout the solar system. These ancient solar wind records, preserved for billions of years in crystalline matrices, provide information about solar evolution and early solar system conditions. The asteroid's atoms continue this process, their implantation in planetary surfaces creating records that future scientists might use to study early 21st century solar activity. The asteroid's dispersed atoms, now streaming away from the Sun as part of the solar wind, contribute to the buildup of magnetic stress in the corona that will eventually trigger coronal mass ejections, billion-ton clouds of magnetized plasma that erupt from the solar atmosphere with the violence of cosmic explosions. These events represent the largest releases of energy in the solar system, each one capable of launching more mass into space than humanity has ever lifted beyond Earth's gravity well. The magnetic field lines that guided the asteroid's atoms through the corona become twisted and stressed by the Sun's differential rotation and convective motions until they reach a breaking point, where stored magnetic energy converts explosively to kinetic energy of accelerated plasma. Magnetic flux ropes form in the corona when helical magnetic field structures become twisted beyond their stable configuration limits, creating spring-loaded systems that store enormous amounts of magnetic energy in their coiled field lines. These structures, invisible except through their effects on coronal plasma and their signatures in spacecraft magnetometer data, can persist for days or weeks before erupting in spectacular coronal mass ejections. The asteroid's conducting atoms, trapped within these flux ropes, serve as passive tracers for the magnetic evolution that leads to explosive instability. Pre-eruptive signatures appear in solar observations hours to days before major coronal mass ejections, as magnetic field lines undergo slow reconfiguration that gradually builds toward instability. Solar physicists monitor these precursor phenomena filament activations, soft X-ray brightenings, and radio emission enhancements to predict when and where eruptions might occur. The asteroid's atoms contribute infinitesimally to these precursor signals through their interactions with the evolving magnetic field structures that will eventually produce eruptive events. Magnetic reconnection drives the explosive phase of coronal mass ejections when oppositely directed field lines in the corona approach each other and suddenly snap together, releasing stored magnetic energy at rates that exceed the total power output of human civilization. This process occurs in current sheet's thin layers where magnetic field direction changes abruptly and can accelerate particles to near-relativistic velocities within seconds. The asteroid's atoms experience these acceleration processes directly when they become caught in reconnection. Current sheets during coronal mass ejection onset. Coronal mass ejection initiation involves the destabilization of large-scale magnetic structures that extend throughout the corona and into the solar wind. The exact trigger mechanisms remain subjects of active research, with competing theories invoking magnetic flux cancellation, torus instability, and breakout models that describe different pathways to eruption. The asteroid's metallic content, by contributing to local electric currents and magnetic field modifications, participates in the complex feedback processes that determine whether magnetic configurations remain stable or evolve toward instability. Plasma acceleration in coronal mass ejections occurs through multiple mechanisms operating simultaneously across a range of spatial and temporal scales. Magnetic pressure gradients drive bulk plasma motion, while magnetic reconnection accelerates individual particles to high energies. Wave-particle interactions transfer energy from collective electromagnetic fluctuations to particle kinetic energy. The asteroid's atoms experience all these acceleration processes, their final velocities and energy distributions reflecting the superposition of multiple physical mechanisms operating during the eruption. Three-part structure characterizes many coronal mass ejections observed by space-based coronagraphs, with a bright leading edge, dark cavity, and bright trailing core that correspond to compressed plasma, magnetic flux rope, and prominence material respectively. This morphology reflects the magnetic topology of the erupting structure and provides clues about the physical processes that drive the ejection. The asteroid's atoms become distributed throughout this three-part structure, according to where they were located within the pre-eruption magnetic configuration. Shockwave formation occurs when coronal mass ejections achieve velocities exceeding the local magnetosonic speed in the solar wind, creating disturbances that propagate ahead of the ejector and accelerate particles to cosmic ray energies. These shocks, analogous to sonic booms but operating in magnetized plasma, can extend across billions of cubic kilometers of space and persist for days as they travel through the solar system. The asteroid's atoms caught in these shock regions experience dramatic acceleration that can boost their energies far above thermal levels. Magnetic cloud signatures identify coronal mass ejections in spacecraft data through their characteristic rotation of magnetic field direction, enhanced magnetic field strength, and reduced plasma temperature relative to the ambient solar wind. These signatures, first recognized in data from interplanetary spacecraft, provide evidence for the flux rope structure of many coronal mass ejections and allow scientists to trace erupted material from the corona to spacecraft locations throughout the solar system. The asteroid's atoms within magnetic clouds carry these distinctive signatures as they travel from the Sun toward planetary encounters. Geomagnetic storm generation results when Earth-directed coronal mass ejections interact with our planet's magnetosphere, compressing the magnetic field and driving enhanced electric currents that can disrupt technological systems. The strength of these storms depends on the magnetic field orientation within the coronal mass ejection, with southward-directed fields creating the most severe disturbances through efficient magnetic reconnection with Earth's northward-pointing field. The asteroid's atoms that participate in geo-effective events contribute to the space weather phenomena that affect modern civilization. Solar energetic particle events often accompany fast coronal mass ejections, accelerating protons and heavy ions to energies exceeding 1 billion electron volts through shock acceleration processes. These high-energy particles, traveling at near-light speeds, can reach Earth within hours of their acceleration at the Sun, creating radiation hazards for astronauts and spacecraft electronics. The asteroid's nuclei that undergo shock acceleration join these energetic particle populations, their trajectories guided by interplanetary magnetic field lines toward various destinations throughout the solar system. Mass and energy budgets of coronal mass ejections reveal the enormous scales involved in these events, with typical ejections launching 1012 to 1013 kilograms of plasma at kinetic energies equivalent to millions of nuclear weapons. The magnetic energy released during these events, converted from stored field energy to kinetic and thermal energy of accelerated plasma, demonstrates the efficiency of magnetic reconnection as a mechanism for explosive energy release. The asteroid's contribution to these energy budgets remains negligible, yet its atoms witness the most powerful explosions in the solar system. Coronal mass ejection forecasting represents a major challenge in space weather prediction, requiring sophisticated models that track magnetic field evolution from the solar interior through the corona and into interplanetary space. These models, constrained by real-time solar observations, attempt to predict when eruptions will occur, how fast they will travel, and what magnetic field orientations they will carry toward Earth. The asteroid's atoms provide additional test particles for validating these models as they trace the complex trajectories of erupted material through the solar system. Multiple spacecraft observations of single coronal mass ejections reveal the three-dimensional structure of these events as they propagate through interplanetary space, demonstrating that simple radial expansion models fail to capture the full complexity of ejector evolution. Advanced missions with spacecraft distributed throughout the solar system provide stereoscopic views that reconstruct the true shapes and internal structures of coronal mass ejections. The asteroid's atoms, distributed throughout these structures, serve as tracers for the three-dimensional evolution of erupted material. Coronal mass ejection interactions occur when multiple eruptions follow similar trajectories through interplanetary space, creating complex collision and merging processes that can dramatically enhance the geoeffectiveness of the combined disturbance. These interaction regions, characterized by compressed magnetic fields and enhanced particle populations, demonstrate the nonlinear nature of space plasma physics. The asteroid's atoms caught in multiple eruption events experience these collision processes, their final properties reflecting the cumulative effects of several magnetic acceleration episodes. Historical coronal mass ejection events, reconstructed from auroral observations, geomagnetic measurements, and cosmogenic isotope records, reveal that extreme space weather events have occurred throughout recorded history, with potentially devastating consequences for modern technological systems. The 1859 Carrington event and 1921 railroad storm represent benchmarks for severe space weather that could cause widespread power grid failures and satellite damage if they occurred today. The asteroid's atoms join the continuing record of coronal mass ejection occurrence that extends back through geological timescales. Coronal mass ejection research continues to advance through improved observational capabilities, theoretical developments, and computational modeling that provide increasingly detailed understanding of these fundamental solar phenomena. Future missions will extend coronal mass ejection observations closer to the Sun and farther into the heliosphere, providing comprehensive views of eruption processes from initiation through interplanetary propagation. The asteroid's atoms represent a minute addition to the vast laboratory of coronal mass ejection physics that operates continuously throughout the solar system. Laboratory plasma experiments attempt to recreate coronal mass ejection physics under controlled conditions, using high-energy lasers and magnetic field generators to study magnetic reconnection, shock acceleration, and plasma instabilities relevant to solar eruptions. These experiments, though conducted on much smaller scales than solar phenomena, provide insights into fundamental plasma physics processes that operate across many orders of magnitude in space and astrophysical environments. The asteroid's atoms experience these same fundamental processes as they participate in the largest plasma physics laboratory in the solar system. The asteroid's atoms, carried by coronal mass ejections and solar wind streams, journey across 93 million miles of interplanetary space before encountering Earth's magnetosphere, a vast magnetic bubble that surrounds our planet and serves as the first line of defense against the constant bombardment of charged particles from the Sun. This magnetosphere, generated by electric currents flowing in Earth's liquid iron core, extends approximately 10 Earth radii toward the Sun and stretches into a long tail that reaches beyond the Moon's orbit on the night side. When the asteroid's ionized nuclei collide with this magnetic barrier, they trigger a complex cascade of electromagnetic phenomena that ultimately create some of the most beautiful displays in Earth's atmosphere. The bow shock forms where the supersonic solar wind first encounters Earth's magnetic field, creating a standing wave in the plasma flow that decelerates and compresses the incoming charged particles. This shock front, located approximately 90,000 kilometers ahead of Earth in the direction of the Sun, operates like the bow wave of a ship moving through water, except that it exists in the invisible medium of magnetized plasma flowing through space. The asteroid's atoms experience their first dramatic deceleration at this boundary, their velocities dropping from several hundred kilometers per second to subsonic speeds as they cross the shock transition. Magnetosheath turbulence characterizes the region between the bow shock and the magnetopause, where shocked solar wind plasma flows around Earth's magnetic obstacle in chaotic, swirling patterns that generate electromagnetic fluctuations across a broad range of frequencies. This turbulent environment, neither fully solar wind nor magnetospheric plasma, serves as a mixing region where particles and energy from interplanetary space gradually penetrate toward Earth's magnetic field through processes that remain incompletely understood. The asteroid's atoms tumble through this electromagnetic maelstrom, their trajectories randomized by magnetic field fluctuations that operate on scales from thousands of kilometers down to individual particle gyroradii. Magnetic reconnection at the magnetopause allows solar wind plasma to enter Earth's magnetosphere despite the magnetic barrier that normally deflects charged particles around the planet. When the interplanetary magnetic field carried by the solar wind points southward, opposite to Earth's northward pointing field, the oppositely directed field lines can merge and create temporary openings through which solar plasma flows into the magnetosphere. The asteroid's atoms participate in these reconnection events, their entry into Earth's magnetic domain facilitated by the fundamental plasma physics process that enables energy and mass transfer across magnetic boundaries throughout the universe. Plasma sheet formation occurs in Earth's magnetotail, where magnetic field lines stretched by the solar wind store energy that can be explosively released during magnetospheric substorms. This vast reservoir of hot plasma, extending from approximately 10 to several hundred Earth radii in the anti-sunward direction, contains particles accelerated to energies far exceeding those typical of the ambient solar wind. The asteroid's atoms that enter the plasma sheet through magnetotail reconnection undergo additional acceleration processes that can boost their energies to levels sufficient for deep penetration into Earth's atmosphere. Ring current development results from the drift motion of energetic charge particles around Earth, creating a toroidal current system that encircles the planet at distances of several Earth radii. During geomagnetic storms driven by coronal mass ejection impacts, this ring current intensifies dramatically and can cause the 100 nanotesla decreases in Earth's surface magnetic field that define storm intensity. The asteroid's atoms that achieve ring current energies contribute infinitesimally to these current systems, their collective motion generating magnetic fields that oppose Earth's main field and create the electromagnetic disturbances measured by ground-based magnetometers. Radiation belt enhancement occurs when magnetospheric acceleration processes boost particles to energies exceeding several 100,000 electron volts, trapping them in Earth's magnetic field for periods ranging from days to years. These radiation belts, discovered by the first artificial satellites in the 1950s, pose significant hazards to spacecraft electronics and human space exploration. The asteroid's heavy nuclei that achieve radiation belt energies become part of the trapped particle population that orbits Earth, their subsequent motion governed by the complex interplay of magnetic drift, pitch angle scattering, and wave-particle interactions. Auroral precipitation begins when magnetospheric particles accelerated by magnetic reconnection, and wave interactions follow magnetic field lines into Earth's upper atmosphere, where they collide with nitrogen and oxygen atoms at altitudes between 100 and 400 kilometers. These collisions excite atmospheric gases to emit characteristic colors green from oxygen at 557.7 nanometers, red from oxygen at 630 nanometers, and blue-purple from nitrogen molecular bands. The asteroid's atoms that precipitate into auroral zones contribute to these ethereal light displays that have inspired human wonder for millennia. Atmospheric chemistry modifications result from the deposition of solar wind energy and particles in Earth's upper atmosphere during geomagnetic storms and substorms. High-energy particles create nitrogen oxides that can catalytically destroy ozone in the stratosphere, while enhanced Joule heating from auroral electrojet currents alters atmospheric density and circulation patterns. The asteroid's atoms that reach the atmosphere participate in these chemical processes, their nuclear charges and kinetic energies contributing to the complex ion-neutral chemistry that links space weather to climate variability. Ionospheric disturbances accompany major geomagnetic storms as enhanced particle precipitation and electromagnetic fields modify the electrical properties of Earth's upper atmosphere. These disturbances can disrupt radio communications, satellite navigation systems, and power grid operations through mechanisms that couple electromagnetic energy from the magnetosphere to technological systems on Earth's surface. The asteroid's contribution to these disturbances remains negligible on a global scale, yet its atoms participate in the fundamental processes that create space weather impacts on modern civilization. Magnetic field line tracing reveals the complex topology that connects different regions of Earth's magnetosphere, allowing particles to travel along invisible highways from the magnetotail to the polar ionosphere. These field lines, which would appear as graceful curves if they were visible, map the three-dimensional structure of Earth's magnetic domain and determine where solar wind particles can access different atmospheric regions. The asteroid's charged atoms follow these magnetic highways with high precision, their motion constrained to spiral around field lines while drifting slowly across magnetic surfaces. Substorm cycle physics governs the periodic loading and unloading of magnetic energy in Earth's magnetotail, creating explosive releases that accelerate particles and drive enhanced auroral activity with typical periods of 1 to 3 hours. These substorms represent fundamental plasma physics processes that operate throughout the universe, wherever magnetic fields interact with flowing plasmas. The asteroid's atoms caught in substorm acceleration regions experience dramatic energy increases that can boost them from solar wind energies to radiation belt energies within minutes. Plasma wave generation throughout Earth's magnetosphere creates electromagnetic fluctuations that can resonantly interact with charged particles, transferring energy between collective wave modes and individual particle motion. These waves, spanning frequencies from millihertz to gigahertz, include phenomena such as Whistler mode chorus, electromagnetic ion cyclotron waves, and ultra-low frequency pulsations that can be detected by ground-based instruments. The asteroid's atoms both generate and respond to these wave phenomena, their motion contributing to the complex electromagnetic environment that characterizes planetary magnetospheres. Oxygen ion outflow from Earth's ionosphere provides a significant source of heavy ions for magnetospheric populations, demonstrating that planetary atmospheres actively participate in space plasma processes rather than serving as passive targets for solar wind bombardment. These terrestrial ions, accelerated by wave-particle interactions and magnetic field-aligned electric fields, can reach the magnetotail and contribute to plasma sheet dynamics. The asteroid's atoms encounter these planetary ions throughout the magnetosphere, creating a complex mixture of solar and terrestrial material in Earth's space environment. Magnetic storm recovery phases can last for days to weeks, as enhanced ring current particles are gradually lost through atmospheric precipitation, charge exchange with neutral hydrogen, and outflow to interplanetary space. During these recovery periods, the asteroid's atoms that achieved ring current energies undergo the same loss processes that restore Earth's magnetic field to its quiet time configuration. Their eventual fate includes precipitation into the atmosphere, neutralization through charge exchange, or escape back to interplanetary space along magnetotail field lines. Seasonal and solar cycle variations in magnetospheric dynamics reflect the changing geometry of Earth's magnetic field relative to the solar wind and the varying intensity of solar activity over the 11-year magnetic cycle. These long-term variations influence the efficiency of solar wind energy transfer to the magnetosphere and determine the frequency and intensity of geomagnetic storms. The asteroid's atoms that enter Earth's magnetosphere during different phases of these cycles experience varying degrees of acceleration and different pathways through the complex magnetospheric configuration. Global magnetohydrodynamic simulations model the interaction between the solar wind and Earth's magnetosphere, using sophisticated computer codes that solve the fundamental equations of plasma physics in 3 dimensions. These simulations, running on supercomputers and validated against spacecraft observations, provide detailed predictions of magnetospheric response to varying solar wind conditions. The asteroid's atoms serve as test particles in these simulations, their trajectories illustrating the pathways by which solar material penetrates Earth's magnetic shield and influences our planet's space environment. The asteroid's atoms that penetrate Earth's magnetosphere and enter the upper atmosphere initiate a cascade of chemical reactions that ripple through the complex molecular environment existing between 100 and 400 kilometers above the planet's surface. Here, in the thermosphere and mesosphere, solar ultraviolet radiation maintains a delicate balance of ionized and neutral species that respond sensitively to the introduction of energetic particles from space. The asteroid's nuclei, accelerated to energies ranging from thousands to millions of electron volts during their magnetospheric journey, collide with atmospheric molecules and create ion-electron pairs that temporarily enhance the ionosphere's electrical conductivity and modify the chemistry that governs trace gas abundances throughout the middle atmosphere. Nitrogen oxide production represents one of the most significant atmospheric chemistry impacts of energetic particle precipitation, as high-energy collisions dissociate molecular nitrogen and oxygen to form reactive nitrogen compounds that can catalytically destroy stratospheric ozone. The asteroid's atoms, carrying kinetic energies far exceeding the binding energies of atmospheric molecules, create cascades of secondary electrons that propagate the ionization process throughout the upper atmosphere. These secondary electrons, slowed by repeated collisions with neutral molecules, eventually thermalize and contribute to the ambient electron population that maintains ionospheric conductivity. Atmospheric heating occurs as the kinetic energy of precipitating particles converts to thermal energy through collisions with neutral atmospheric constituents, raising local temperatures and driving enhanced atmospheric circulation that can influence global climate patterns. The asteroid's contribution to this heating remains infinitesimal compared to solar ultraviolet radiation and auroral particle precipitation. Yet its atoms participate in the same fundamental energy deposition processes that couple magnetospheric dynamics to atmospheric structure. This energy deposition creates temperature enhancements that propagate downward through the atmosphere and can influence circulation patterns in the stratosphere and troposphere below. Ion-neutral chemistry in the upper atmosphere operates through reaction networks of extraordinary complexity. involving hundreds of chemical species and thousands of individual reaction pathways that determine the abundances of trace gases throughout the middle atmosphere. The asteroid's atoms, once neutralized through charge exchange or electron recombination, become part of these chemical networks as reactive atomic species that can initiate catalytic cycles affecting atmospheric composition. Their heavy nuclei iron, silicon, and magnesium introduce metallic species that form exotic compounds rarely encountered in terrestrial chemistry. Mesospheric metal layers result from the continuous ablation of meteoritic material in Earth's upper atmosphere, creating reservoirs of metallic atoms and ions that condense into nanoparticles and influence atmospheric chemistry and physics. The asteroid's heavy elements join these existing metal layers, contributing to the population of cosmic dust that serves as condensation nuclei for noctilucent clouds and influences the radiative properties of the mesosphere. These metallic species undergo complex chemistry involving cluster formation, oxidation reactions, and photochemical processes driven by solar radiation. Hydroxyl radical production increases when energetic particles dissociate water vapor molecules in the upper atmosphere, creating highly reactive OH radicals that participate in ozone destruction cycles and influence the oxidative capacity of the atmospheric chemical system. The asteroid's hydrogen nuclei, having carried water's components from their original icy reservoirs, contribute to these hydroxyl production processes when they recombine with atmospheric oxygen species. The resulting OH radicals can propagate downward into the stratosphere, where they participate in catalytic ozone destruction cycles that influence Earth's ultraviolet radiation environment. Stratospheric ozone depletion occurs when nitrogen oxides produced by particle precipitation descend from the thermosphere and mesosphere into the stratosphere, where they catalytically convert ozone molecules into molecular oxygen through well-established chemical cycles. Each nitrogen oxide molecule